Okay, so in this video I'm going to talk a little bit about force versus displacement graphs. And I already have a graph up here which represents a force versus time graph, which we talked about earlier in the class. And the idea here was that you could graph the component of a particular force over some amount of time. And the area under the curve, if you all remember, was the change in the momentum in that direction. And that can be both positive and negative depending on whether you're above or below sort of the y equals 0 sign here. So this is another, let's say that's 1 and that's 2. This one's greater than 0 and this one's less than 0. So anytime you have an equation that has this sort of structure of the product of two things, when you think about the graphs, the area under the curve is the multiplicative product. Okay? The nice thing about this was we could do these graphs in each coordinate direction because you could graph Fy and Fz, and you could look at the change in momentum in each of those directions. When we're talking about the work done by a force, we're taking the dot product of that force with the displacement. And unfortunately, that loses a little bit of information about what the direction of the force is and what the direction of the displacement is when you do this sort of dot product. You end up with a scalar, a number. And so these force versus displacement graphs are kind of restricted to when you have to worry about a particular direction, let's say a force in the x direction, and you're looking at the displacement in x, you can't change these to other situations. It has to be motion on a line because the area under the curve tells you about the work that's contributed by that coordinate direction. So you can add these up. You could do, fx delta x plus fy delta y plus fz delta z. And you could calculate the work that's done by the force in the z direction, the work that's done by the force in the y direction, and the work that's done by the force in the x direction. But that's a very sort of kludgy way, and it's actually not the way that people think about works. So oftentimes we're going to avoid the idea of, when we're talking about these kinds of graphs, we're going to just say that the motion occurs along a line, and we're going to worry about the force in the x direction and the displacement in the x direction. And so if we do some sort of similar type of graph, like this, let's say, then the area under this curve tells you about the work that's done over that displacement. So this would be the work that's done in, say, in going from 0 to x1. And this would be the work that's done in going from x1 to x2. And similarly, the area under the curve is the work that's done, but it also has a sign. So it's above the fx equals 0 line. This is a positive work that's done. This is the negative work that's done. And you can determine the total work that's done by adding up those two. So the total work would be, what is the net area under the curve? So it would be 1 plus 2 and so forth. So you could have multiple of these. This is a pretty useful tool for thinking about how the kinetic energy changes in various ways. We can play the game of starting off with a particular amount of kinetic energy and predicting what the final is by looking at these kinds of graphs. This is just another way of representing the kinetic energy work theorem by looking at how the kinetic energy changes over the displacement, which is a result of the work that's done by the surroundings. So in the next video, what we'll do is we'll talk a little bit about what happens when the forces change more continuously. We're going to step away from this idea of graphing and go back to a mathematical formalism. But this idea is very powerful to think about how the kinetic energy would change in a different type of representation.